Okay, now that we have prepared the one-hot data, we can finally do multiple regression on all of Amy's house pricing. Notebook 05A, loading the data. Here we go. Multiple regression with sklearn. Choose the independent variables that we want to use. varsind should contain all features from varsind numeric and varsind one-hot. Well, that makes sense. We're going to include all the features that were originally numeric, like lot area, and we're also going to include all those 100 and whatever it was, one-hot columns that we created from the categorical variables. Actually, before we continue with that, I've just noticed up here that we are doing something interesting with the data. If you remember, at the end of the previous notebook, we created a variable called fold, which could take the values 0 through to 9 inclusive. So that variable, which was random, basically divides the data into 10 pieces. And here in IDX train, we're including pieces 0 to 5 inclusive, 6 of the pieces. Another 2 parts of the data are in IDX val. So we have train data, we have a validation data, and the last 2 parts of the data are in test data. I'm not going to go into that much more, but you're going to see that we're going to fit the model on train, and we're going to see whether the model performs on other data, maybe the validation data, maybe the test data. We'll talk more about train, test, and validation in a while, but right now we're just doing that to know whether our model is any good whatsoever. But now that we're holding out some of the data, there will be some data, val and test, which the model has never seen, that we can use to test our model. Here we go, varsind. Varsind numeric plus varsind one-hot. It's interesting, by the way, how you can use the plus sign to add 2 lists together, end to end. The plus sign is obviously normally used for adding numbers. Now, prepare the X and Y model matrix. This is obviously going to give us an array, 1 row for each house, 216 columns for all the variables we're interested in, and Y, vardep. If you remember, we defined vardep to be the sale price. Transform separately the train and validation data. That sounds like a really bad idea, actually. Sorry, I didn't notice that. It said create a standard scalar and fit it on over the training data only. That's fine. As always, we instantiate it, then we fit it, and finally we transform. Good. Fit the model. Well, we've done this a few times now. Hopefully you're getting used to what we need to do. Import the class that we're interested in. Sorry, that should have read from sklearn linear model, import linear regression. And finally fit the model. Well, easy, right? Sorry, I needed a values up there, otherwise it was going to stay as a series, and it's a little bit different if I want to slice a series. Good. Create some predictions. Well, that should really not be too hard. I hope you managed to give that a go. We have done this before. What is the mean predicted, let's say, on the train data? p.mean. I'm just going to round this. p.round. Right. Now this is interesting. The mean predicted sale price is not the same as the mean actual sale price. And I've written a comment down here. The code doesn't give the correct predictions We're going to see later on that this model is a crazy model. The coefficients are insanely huge. We'll try to understand why that's happening, but I suspect that is causing some problems, and that's why the prediction mean is not correct. Can we reproduce a prediction? I've done it for you. This is the first prediction, which we used sklearn predict to create, and down here we can create a prediction which is just the intercept plus the coefficients dot product with the first line of the training matrix, which is the information about the first house. So we are simply multiplying each coefficient with the relevant feature. Okay, and very strangely that's not working either. I do hope that is to do with rounding errors. Let's find how well we perform on train, val, and test. We should certainly find that this model performs very well on the data on which it was trained. There were, after all, 216 columns now to predict the prices of just some 2,500 or so houses. So you haven't quite got a column per house, but you do have a lot of columns. Let's find the train error using our function above. This is the mean absolute error. If you remember, I think when we did this for the first time with only a few variables, the error was around about, was it 20,000? Something like that. Maybe 27,000 even. Train error is just under 13,500. However, when we try testing our data on validation data, we get 15,000, and on the test data, we get 16,000. So we are seeing a much lower error, a much lower prediction error on the data we used to train the model. This is called overfitting, and that's what we're going to talk about at the beginning of week 3. This is an attempt to look at it using graphs. I'm not sure if these graphs are massively helpful, but on the training data we could possibly see that the actual unpredicted are more closely together, and on the validation they're more spread out. Now let's look at the coefficients. Once again, dreaded typo. Whoa! Look at this. Basement square foot, minus 1.2 times e to the 16. These coefficients are huge. They can't possibly be sensible. That if for each square foot of basement that you have, your house gets cheaper by a few billion dollars. That doesn't make any sense whatsoever. What is happening here? Well, I think two things are happening. Possibly some of these variables are highly correlated, and when variables are highly correlated, linear regression or traditional linear regression finds it very difficult to converge to a sensible solution. The other possibility, and we're going to talk about this next week so you don't really need to understand it now, is that there could be a lot of overfitting going on now. That is it for traditional linear regression. We are next going to move on to penalized regression. See you soon.